Okay, so this class in many ways is like General Chemistry 2.5. We're going to take what we already know and then we're going to build on it. And one of the things that we already know is how to find equilibrium concentrations. They can be found a couple of ways. We're going to do two things. We're going to look at concentrations of things that are in solution and stay in solution. But we're specifically also going to look at things that come out of solution and then see how to get them out, and then how to get them out selectively, leaving everything else behind. And then the wrinkle of, is the other thing that's in solution changing the value of what our textbook tells us to be expecting, which is a real thing. Okay. So in the simple sense, there were two things that were important in Equilibria, and they were weak acids and insoluble or sparingly soluble salts. Let's look at both of them. Okay. We'd seen things like hydrofluoric acid is a weak acid, very, very different than its cousin HCl, because cousin dissociates 100% as a strong electrolyte, puts all of that H plus into solution, puts all the Cl minus. And for general chemistry 2, we didn't care about the chloride. We absolutely didn't. That's the acid part of the solution, and that's the only thing that's important, because when I know that, I can find pH, and then I can talk about all sorts of other things. And then we get to organic, and this is all we care about. It's the H plus. It's not the counter ion. We call that the counter ion. It's just the thing that's helping put the H plus into solution. And we are told that this is such a strong electrolyte that there's nothing you can do here to make it reattach. That those the H pluses and the Cl minuses don't want to reattach to ever come back to being Cl, which may or may not be true. On the other hand, HF only puts some of its H plus into solution. We talk about basicity, that the chloride ion is a weak base, the fluoride ion is not a weak base. It's bases that make bonds. If that base can make a bond to this acid, then you go back and you make this. If this is an acid and that's an acid, then we're going to have a problem, because we're calling this two different things by the same name. That's the acid. H plus is the acid. They call that the free acid. Okay. And the amount that gets to put into solution, K, which is product of reactants, gets to be the product side divided by the reactant side. Because this is now the acid dissociation constant, that gets to be Ka. All right? And they have values, and There's only a value of Ka if it's a weak acid. If it's a strong acid, then it's all products divided by no reactants. And when you take a number and you divide it by 0, you get infinity or a number close to it. So that's of no interest to us. It's not part of the equilibria scene. So only for weak acids. And we see numbers in the 10 to the negative 5, 10 to the negative 8, sometimes lower, but not a lot. Okay? So functioning weak acids have Kas in the 10 to the negative 5, 10 to the negative 8, something like that. Okay? Other things to know. Carbonic acid is a diprotic acid. It has 2 H pluses. That it delivers into solution in 2 steps. And we call those Ka1 and Ka2. If you look at the overall, oh, there's a negative there. Hydrogen carbonate appear on the left and the right hand side. So they cancel. And these protons appear twice. So they add, and the carbonate only appears once. So line 1 and line 2 add, when you add them, the value of Ka overall. What did we do to Ka from these 2 numbers? Yeah, they turn out to be the product. Ka1 times Ka2. This is before we've put any numbers to them. Oh, when I got locked out of my office, I got locked out without my phone. My phone is there. You could quickly look up the values of Ka1 and Ka2 for carbonic acid. It's all in a table in the book somewhere. If you just said carbonic acid, Ka, it would probably tell us.
Ka1 is 4.3 times 10 to the negative 7th.
Yeah.
And Ka2 is 5.62 times 10 to the negative 11th.
Mm-hmm. Okay, so here is what we were talking about a minute ago. This is a functioning value of a weak acid. It is something times 10 to the negative 7. It's not a lot, but it's enough to put H plus into solution and therefore be an acid. The value of the next dissociation constant is how much smaller? 10,000 times smaller. Each of the exponents represents what it says it represents, a factor of 10. And the difference between 11 and 7 is 4. So the difference between our numbers is something that has 4 zeros in it. This is 10,000 times smaller than that one. Why?
Because it's harder to pull away an H plus from something with a negative. So H plus is pulled away from the negative.
The deal is there is no charge here. I'm creating a new separation of charge, which nature never really likes, but we get away with it if we balance the electrons right, and we have closed shells here when we don't there, or stuff like that. But to generate another positive away from something that's already negative, now that's a fight. Because positives and negatives attract each other. Okay, so that positive is here, it's still attached, is attracted, doesn't want to go. It's 10,000 times more difficult. So our overall, multiply those two numbers by themselves. That will give you the Ka overall for this reaction, for this total dissociation. This is one of those things where what you were told in high school isn't true.
2.4 times 10 to the negative 17th.
Okay, this is a really, really small number. To go from here to there, it's going to be difficult. What this is telling us is this one doesn't contribute significantly. And if it doesn't contribute significantly to the H plus that's in solution, are you sure you want to be including it in your calculations? Okay. So, general chemistry tells us that carbonic acid loses both of its H pluses because that's what stoichiometry tells us. Chapter 3 of the book, it's got two H pluses, therefore that's how it falls apart. It's much more likely to stop here and give you one H plus and make the hydrogen carbonate. There are times, though, if we put it in base, that the base could pick those H pluses up, that it will go all the way there. So what we're going to have to do is decide under what conditions will this say, that wasn't too hard, and under what conditions will we force it to give everything that it has. Okay? That's in our immediate future. Questions? So there's a couple of things that we did in weak acid equilibria. That first step. Okay, so we're deciding that this is the source of most of the H plus that's in solution, not step number 2. So when you are asked how much H plus is in solution, you figure whatever number this is, whatever number this gives you, the second line of the multiple equilibrium is 10,000 times smaller. So when I go and find my value of H plus and find out that it is 0.0125, a number that is 10,000 times smaller than this number is at the tenths, at the hundredths, at the thousandths, at the 10,000ths position. And I don't have any recorded precision for that number. Okay. We let that one go until we do have recorded precision and we have to keep it in. Okay? So, there will be times when the number will make sense because it has to, and then there are other times when we let it go. The other thing that we're going to let go is that the K is that divided by this. And we have decided, or we have found that that number was, it was 4 something times 10 to the negative 7. Yeah? Now, if this is 0.1 molar, then that's my number that I start with, 0.1 mole per liter. And then we're going to say that the distribution in these numbers is so bottom heavy that it is 0.00000004. 10 to the negative 7 means, which means that the amount that I'm losing from this, my initial concentration, the amount that I lose from my initial concentration at equilibrium is so puny that I may as well just say this. And that was a really, really beneficial approximation for us, because when we approximate that, it means that I don't have to account for the amount that I have lost to the equilibrium, which means I don't have to have a quadratic solution. It means that the number just pops out, okay? There are times when, and our general chemistry textbook does that horrible thing where it says, if you want to know whether you use the quadratic solution or the approximation, do it the long way, and then do it the short way. And if the numbers don't make any difference, then you could have just done it the short way, which is not how any of us are going to work. If the number is more than, there's a little kind of rule of thumb that if the concentration value is more than like 1,000 or 10,000 times bigger than this, it doesn't work 100% of the time. That's why it's not in the book. Then just go ahead and do the approximation, right? And 0.1 is more than 1,000 times bigger than 10 to the negative 7, and it's more than 10,000 times bigger, so we're probably okay. I'm not sure if it's our book or there's one book out there that I used at some point where it says, see this is why we don't use it, because in this scenario with these chemicals, that approximation works. With these ones, with the same, what looks like the same numbers, it doesn't. But it's a useful thing. Okay. The other thing that we're going to use Equilibria for is for precipitations. So if we do find the concentration of an ion in solution, it's probably a weak acid or the salt of a weak acid, because those are really useful. Precipitations are going to be solubility products. We saw these on Thursday, that I will have a solid that is sparingly soluble. And the question is either how do I keep it in solution, or more often, how do I get it out? It turns out that a lot of the simple ions that are insoluble are toxic. So think, all nitrates are soluble. Most chlorides are soluble, except lead, cadmium, mercury. These are all heavy metals that we do not want in our water supply because they are toxic. So there is a real application of, I want to find out how much dissolved lead is in my water supply, and I want to remove it using the minimum amount of reagent, because one, I don't want to spend a lot of money, and two, just throwing chemicals at a problem is not always the correct answer. And one of the things that we will learn in this course is there are unintended consequences of having ions floating around in solution that are spectators, that we have been told up to this point do not contribute in any way to what's going on in the reaction, because that's not true. Spectator ions for chemistry 1 are not spectator ions in chemistry 3401. Okay, that's a solid. These can be in solution. That cannot have a concentration, but these two can. So when I find my value of K, which is products over reactants, so by definition, solubility products are always written as the insoluble salt going into solution. They're not written as these ions making a precipitate. They're always written products over reactants, because then we don't have an inverse. Oh, what on earth did I write? Not iodine, 2 iodides. So I have 2 iodides stoichiometrically in my equation, which means I get to square that, and then all divided by the lead iodide, which is a solid. So my answer is just the ions. What's it called when you add 2 numbers together? Did we do this already? It's called a sum when you add 2 numbers together. What's it called when you subtract 2 numbers from each other?
The difference.
That's the difference. And when you multiply 2 numbers by each other?
Product.
That's the product. So when this gets to be the solubility product, KSP, solubility product, the product just means take those numbers and multiply them by each other. It doesn't mean anything more than that. Okay. All right, we should probably throw some numbers. In the lab, if I'm going searching for a concentration in solution, how am I going to find that?
Do we have numbers of others?
Do we have what?
Another, and then just stoichiometric, can we figure it out? Like do a titration.
Titration? Titration is absolutely one way. So experimentally, how am I going to find the numbers that are in solution? Okay, 2 big ways. am I going to find the concentration of my ions in solution? Titration. We did a couple of titrations in chemistry 2. There's a titration in chemistry 1 now. Yeah. There should always have been, and it was missing for a few years. We looked at the shapes of curves. There was a lab that just basically looked at the shapes of curves and found strong acid, strong base, weak acid, strong base curves to see how they change. And we did, there was one that was KSP, calcium hydroxide. And there was another one. There was one where we found, we did a half titration. Titrations are actually so easy that you don't need to complete them in order to know what's going on if you think deeply enough about what the numbers mean. Okay. So typically, if our unknown ion is from a weak acid, we would do an acid-base titration. Okay, and we get different titration curves. This is volume, this is pH. If I add acid to base, strong acid to strong base, what's the shape of my pH curve, what titration curve look like? So if I add strong acid to strong base, my pH runs 14 to 0, 7 in the middle. pH of a strong base is going to be about 14. And what happens is when you add acid to it, you make very little impact in the pH. It's a log scale. So you are making a difference, but it's not reflected in the scale. And then it starts to bend. And then all of a sudden, you're here. And then it levels off and ends up that way. And we can put a line through it. And the point at which the curve stops inflecting that way and starts inflecting that way, right here, is the equivalence. And when you have a strong acid and a strong base, then your equivalence happens at pH 7. Okay. Our computers, the vernier equipment, can differentiate that graph. And instead of us seeing that the curve changes from being, let's call that one convex, to being concave, it will take the differential and say, well, here's the turning point, and the turning point is your equivalence point. And it will also do the second differential, which goes that way, and where it crosses the midpoint, that's your turning point. If you've got good data, this one should be better than that one. If you've got bad data, this one might be better than that one. Okay. What happens if I add a weak acid? If I add strong base to weak acid?
It'll
What does the curve look like? this is where my strong acid is. Weak acids are here. And I get the same thing. And then can't go any higher than 14. So now my curve goes here, and the equivalence will be above 7. If I added a weak acid, a weak base to a strong acid, my equivalence would be below 7. Do a couple of things that so that we know that we can do them, and then we'll look a little bit harder. Okay, I've got monoprotic weak acid. This is from a previous exam. This was a 4-page question from a previous, yeah, it's all on one topic. Four pages.
Are you going to give us a 4-page? Are you
Yeah. Am I what?
Are you dropping a hint?
Yeah. Well, I'll tell you what the questions are. Here's the Ka. Tell me what the pH, what the H plus concentration is. Okay, that's easy. At a particular concentration. Now dilute it a lot. What's the new concentration? What's the new acid concentration? That one's quadratic. And then it says add an ionic contaminant.
To the diluted solution?
Yeah. Yeah. What happens now? And then it says add an ionic contaminant that is the common ion of what's already there in solution. What's the H plus now? Okay. 4 pages. Yeah, but it'll be take home. It's a take home test. I'm not gonna. These are far too these questions are far too complicated to do in class.
Wow, thank you.
5.6 times.
Much appreciated.
So we do it Thursday or?
You'll get the test when I've either covered ionic contaminants, probably not, or selective precipitations. Yes, which I think I'm going to do first. So we'll do this just so that everybody knows how to find an equilibrium value, and then I'll do selective precipitations because that's useful and we have a lab for it. And then I'll give you the test. Ka is 5.62 times 10 to the negative 4. Okay. Tell me about the acidic trend of acidity of nitrous acid.
It's kind of acidic.
Yeah, it's actually a pretty good weak acid. 10 to the negative 4 is a pretty good acid. All right. Write the equilibrium constant expression for the weak acid dissociation of nitrous acid. Assume that the amount of nitrous acid that dissociates at equilibrium is much smaller than the amount of undissociated acid. Calculate the equilibrium concentration of hydronium ion in a 0.15 molar solution of HNO2. All right, here's where it gets a little bit tenuous. My dilute acid has a concentration of 0.15 moles per liter, but its Ka is not a small number. It's not a small number. So just assuming that I'm going to do that approximation that we did over and over and over in chemistry 2 might be an unsafe assumption, okay? Because this is only 1,000 times, in fact it's about 500 times smaller than that. So let's do it anyway. I'm going to go initial, change, equilibrium. Yeah.
Reverts back in time.
The initial amount of HNO2 in solution is 0.15 moles per liter. This is 0, and that is 0 because it hasn't gone into solution yet. At equilibrium, some amount of H plus breaks away from the free acid. So 0.15 minus X. Oh, I'm sorry. That's getting ahead of myself. I'm going to lose some. And because this is a cation, that's an anion, they are intrinsically linked together. This number is not going to be different than that number. So when one of these pops up, one of those has to pop up. When two of these pop up, two of those has to pop up. And so my equilibrium value is 1.0.15 minus the amount that I've lost, X and X. Ka is 5.62 times 10 to the negative 4, which is equal to the concentration of the reactants, products, divided by the concentration of the reactants. Okay. So 5.62 times 10 to the negative 4 equals X times X. So I've got X squared on the top, divided by 0.15 minus X. Here's where the payoff comes. We say that that is approximately equal to this. I'm going to say that that is an insignificant amount. Probably not true. But it does make X squared equal over 0.15 is equal to 5.62 times 10 to the negative x squared is 0.15 times 5.62 times 10 to the negative 4. So x is the root of that. And your answer is
I got 0.0091.
I know that too.
okay. That value of x represents the concentration of H plus. So if I wanted to find pH now, I could. All right, follow-on question. This gets diluted to 0.0015. Now, that value of Ka is a little bit close to this, because that's this right here is 0.000562. They're not very, very different anymore. So when your value of Ka is 10 to the negative 8, you really don't have to worry about dilution, because you would have to worry about dilution being really, really, really dilute. But here, where I've got two things. Two things that are conspiring is that this is now a very dilute solution, and that this is not that weak. Which means that this is no longer insignificant. The amount that we lose into equilibrium now has to be counted. Okay. Everything is set up the same way, except this is now 0.0015, 0.0015, 0.0015 minus x. Okay. What you have to do is rearrange all of that until you make it fit the quadratic template. What's the quadratic form for an equation? Yeah. Yes. Equals
Zero.
0.
Oh, 0.
So we need this information to be transformed to be ax squared plus bx plus c equals 0. your x squared.
You want to get the things out of the denominator first and make it into bx and c and multiply them out.
That multiplied by that.
Yeah, it just becomes negative.
And that. Yeah, but I might choose
Yeah,
to
move it.
move it across the
It was
equal
that.
sign in a minute. I don't know what that number is, but I've got minus 5.62 times 10 to the negative 4x. And then whatever those two numbers multiplied by each other are.
I got 8.43 times 10 to the negative 7.
8.43, yeah. Okay, so that now equals x squared. Do I just shove them all on the other side?
Kind of, but not really. You have to subtract or add them.
Mm-hmm. Yeah, that's kind of, well. So I can just leave the x squared where it is, yeah? And then I'll move this over, because this is, okay. And this will now become plus 5.62 times 10 to the negative 4x. And then this becomes negative. I leave nothing on this side. Minus 8.43 times 10 to the negative 7. So there's my ax squared, there's my bx, there's my c, now all equal to 0. You're going to do it by hand, or are you going to stick it into your calculator?
Calculator, that work, I don't want to do that.
Okay, because x is negative b plus or minus the root of b squared minus 4ac over 2a.
That's funny. It's funny that you think that would do that.
But all your calculator wants from you is you tell it quadratic and it asks you, what's the value of a? And you say the value of a is 1. And what's the value of b?
5.62.
Yeah, that's an x. And then what's the value of c? And you put the negative in.
See, you guys are stupid. You have to go to math, scroll up 1 to 8, you'll see a thing called solver. Enter.
Hold up, you said math, then go to 8?
I think, or the very bottom, like the very, very bottom.
Oh, I see solver.
And then get that, that's 0 equals, you plug in that entire equation.
Beautiful.
Yeah, into that.
Why did we get the 8.43 again?
That's multiplying this number by that number.
Okay.
So I've got this is 0.0015 minus x, all in a term right here. And I'm multiplying this number into it. So I'm going to multiply that number and I'm also going to multiply this value. So it holds the x and it carries the x's with it.
Asking me x is equal to.
Yes, you just push, well, just like put a random number in, like 1 or something. Just put 1 and then hit alpha and then solve. Well, alpha and then the bottom right, the enter button, there's a little solve on the top right.
Got you.
Did you get 6.79?
No. I don't know what he gave.
Let's see.
did. The hard way.
Oh, he has it on the board too.
Wait, actually? Oh.
Oh.
Oh, I don't know that.
Let's go ahead and erase this.
I thought 6.79, Dr.
Yep.
Myers.
6.79 watts times 10 to the. Are you telling me 6.7?
Oh, okay. -4. Okay, it did not show me the 10 times 10 to the -4. I
Yeah.
scroll all the way to the right. Okay, we're good.
Okay, I'm gonna clear away.
Because you cannot put a dilute acid into solution and generate
I was
6.7 molar.
I was like, there ain't no
H
way.
plus.
I was like, I'm doing something wrong. Yeah, you have to scroll. If you, yeah.
I'm looking for a table in the book.
I'll do it for you. That's 5.6. Yeah, that should be right. So enter alpha.
Okay.
Plus 5.62, yes.
It's so funny every time we use our calculators, I say two different things.
So there are two solutions to a quadratic. One of
Yeah,
them will be
So
nonsensical.
yeah, the thing
One of
with-
them will be a negative number.
Yeah,
Just
the
ignore
thing
it.
with the frickin' the TI-84s is that they they ask you for some random number.
Yes.
And they'll give you the X closest to that random number.
Yeah.
So I'm just like.
Yeah. So you really need to know how to use your calculator.
I really do.
Okay.
It's so long.
These are the two kind of starting places for solution chemistry. Let's look at one for precipitation chemistry.
Don't give me.
Yeah, I'll figure it out later. Future.
That makes me so mad. Okay.
I did get that. Yay. Fractional precipitation.
Yeah.
Oh, boy.
Did you say boring?
I said boy. Oh boy. I'm a little nervous.
Let me see if I've got any numbers that I can just pull. Okay, we can start this. So what I'll do is I'll give you a question, but it's not the real question that I want to ask. Let me see if there's an appendix in the back. What I want is a table of solubility products. And we can go ahead and ask kind of the chemistry 2 question, which is, which one of these precipitates first? And then, hey, oh, here we go. Which one of these precipitates first? And at what concentration do I have to add reagent to make the first one precipitate? The follow-on question from that is, are you sure? Are you sure that only one thing has precipitated and not both things? Yeah. Okay. So Appendix F in our textbook has bunches of chemicals. Let's look at some hydroxides. Oh, they did an interesting way of doing it here. They have Everything counts as being L, a ligand.
Huh?
Yeah, they don't write the chemical formula of the precipitate out. They tell you in what stoichiometric combination it goes with the ion that you're interested in.
A ligand? How do you spell that?
Ligand.
You're gonna love that. And sound like one day you would take it.
Yeah, maybe one day.
Or in inorganic is more fun.
Iron hydroxide, cobalt hydroxide. How about that? There you go. Iron hydroxide, 1.6 times 10 to the negative 39. Cobalt hydroxide, 3 times 10 to the negative 45. .6 times 10 to the negative 39. KSPs can be really, really tiny.
That is practically impossible, right?
No.
Okay. What did you say? I asked if that's practically, like, if we're to, like, actually get.
Well, it's got 2 digits of precision there, so that tells you somebody really measured it.
Feel bad for that guy. Or girl. Who did that?
All right. All nitrates are soluble. So if I have a solution of iron 3 nitrate, we're establishing that the question is about cobalt 3 and iron 3. Hydroxide is an OH minus, just 1 anion. If I have iron nitrate and cobalt nitrate, they are guaranteed to be soluble in water. I want to separate them from each other. So I have a mixture of this and that, both soluble in water. And you could invent a number. We can put a concentration in here, like 0.1 mole, right? Question is, how do I separate them?
You said, oh. Wait, what do you want to separate?
Right now, I have a solution that has iron and cobalt in it. I want to just separate them. I don't care how. I just want the iron to be in this flask and the cobalt to be in a different flask. How do we make that happen?
Well, you precipitate it.
How?
By putting hydroxide.
Most hydroxides are insoluble. It's really only the group 1 hydroxides that are soluble. Even the group 2 hydroxides have all sorts of solubility problems. So I'm going to add hydroxide. Do I just splash the hydroxide in there?
No, because if you splash a ton of hydroxide in there, you might also get cobalt to precipitate.
So I might shock them both into co-precipitating. So I'm going to add this slowly, dropwise.
Hmm.
And I'm going to raise the pH until one of those things precipitates. Which one precipitates first?
The iron.
I can. It will make absolutely no difference to me.
It
Yep.
will?
Yep, yes, on the board.
Oh.
Huh?
Is it based off of the KSP one?
What does KSP tell us?
The solubility products.
Okay.
So iron co-occur?
Iron, because it's a smaller KSP.
This one versus that one.
Yes.
Which one's smaller?
Iron.
Is it?
Smaller!
Oh my god, that was weird.
That was really weird. It was so sad.
So sad.
I know. And what's funnier is that the fact that you think about we're being recorded technically.
They don't know me. Oh my god. I think we need to cut the camera off.
Yes, yes.
If you add hydroxide, drop-wise, we should get to a point at which the salt with the lowest, smallest KSP precipitates and leaves the other one behind. Now, if that number was negative 39 and this number was negative 38,
Oh, yeah.
chances of you separating them is slim. But how much difference are they?
So,
That's
would that
about.
be like 6 times 10? I mean, not times 10. Would that be 6 zeros?
Yes. So,
What is that?
The
million.
difference between 45 and 39 is 6.
That's a million.
That represents 6 zeros. One of these is 1,000,000 times less soluble than the other one. So if you did this carefully, maybe you can separate them. Okay. Which one precipitates?
The cobalt.
Cobalt.
It's the smallest.
Okay. Question. How much hydroxide do you have to add to make the cobalt precipitate? All right, let's start with this being 0.1 molar. 0.1 molar. Actually, I'm gonna change the question. Because we have a point at which it starts and a point at which it ends that we don't know about yet. So let's just go with ballpark. How much do you need?
Wow.
We're gonna write the KSP as an equilibrium. Okay. Then you write its value of KSP. The value of KSP is known. The cobalt is known. Because we just invented it. Okay. That should be square brackets, because it's still a concentration. Okay, so the concentration of hydroxide cubed is 3 times 10 to the negative 45 divided by 0.10. Just moved it over. So the cube root of that fraction is equal
3.1 times 10 to the negative 15, sorry.
3 times 10 to the negative 15. Okay, that's not a lot. Just making sure, I don't know, because we make this one up.
Oh.
I don't know what the number is. Get the same number? Okay, then that's a number. On Thursday, we will ask are you sure? Because yes, that might be the concentration that is required to make the cobalt precipitate. The question is, did it take any of the iron with it? So we'll take this value and then cycle it back into the question to see that either the iron has been left alone or it's also come out of solution. Okay? And we do that by inventing sets of concentrations that are not at equilibrium. Q. And if Q is larger than K, SP, then your stuff precipitates. And if Q is, did I say less than? Okay. And if Q is less than KSP, then your stuff hasn't precipitated yet. Okay? All right. We'll see you Thursday.
Dr. McGuire, about the honey farm, do we know any more about how it's happening on Friday or not happening on Friday?
I need to know what your schedule is.